Hello. This tutorial is about calculating dynamic melting outcomes using the pyusercalc Python package. While the package is primarily set up for porous flow melting calculations, it is sometimes useful to compare those results with Dan McKenzie's method, especially to compare with the literature. There are a few reasons why I think the older dynamic melting method is not quite as mechanistically realistic as porous flow, which I do want to mention here. Dynamic melting assumes a fixed threshold or critical porosity as a mass or volume percent. Below that threshold, all melting is actually batch melting or equilibrium melting. And above the threshold, it's perfectly disequilibrium, fractional melting, though both over time. While this approximates having a trapped and interconnected pore space regime, it's probably dynamically less accurate than a liquid flow with continuous chemical equilibration, where you can scale the amount of equilibration. Our porous flow model allows for chemical disequilibrium transport, scaled as a Dam-Kohler number. We do think this is more accurate, but we also know it is sometimes very helpful to compare porous flow results to dynamic melting in older studies that use it. So we've written a Jupyter notebook that calculates dynamic melting in a way similar to the formulas in Richardson and McKenzie's paper, and also Zou's formulas. We actually tested this tool using both sets of formulas and confirmed they come out the same. We also generate outcomes that match calculations from Andreas Strachey's 2003 incremental calculation tool without being as computationally onerous or as expensive. The inputs for this script are the same as for the porous flow tools in pyusercalc, so you can use exactly the same input file in a data folder as you would use for the pyusercalc calculations. I will just quickly walk you through the code for dynamic melting. It's this notebook here, pyDynamic, currently version 1.0, though in the future there might be updated versions you can try, which should look similar. I'll walk you through this and show you how it runs, just so you can see how to set it up. This one can generate a full one-dimensional calculation column that saves at every pressure, as well as batch calculations that save the final outputs over a range of input conditions, so you can compare directly to pyusercalc calculations. It looks like I've run this before, so I'm going to restart and clear output so that I know I'm doing a fresh calculation and not opening something old that isn't actually running. The first thing I'm going to do is run some of these cells to set up my calculations. It looks like I've turned this one off by commenting it out just so that it's quick to run, because I'm going to run my sample input file multiple times for testing, so I'll skip right to that one. You could also run this by removing the comment, and then it will ask you a question instead where you can type in a response. Either works. The next cell sets up file directories, and then tries to locate your input file so you can view it, make sure it looks correct, and display it as a table and a figure so you can see it in a couple different ways. Then there are a few things that are more inline in this notebook than in usercalc, because they have simply not been put into the pyusercalc driver script as a class or as part of the existing classes. So here, running this cell saves the function that you're going to actually use to do the calculations later. You need to do that relatively early in the process, so we just put it right up at the top of this script. The next few cells let you modify your inputs for transport or decay through the lithosphere. This is set up exactly the same as in the pyusercalc notebook, so I'm not going to focus on it here. I'm just going to breeze through all this and say that we are going to stop melting at the base of the lithosphere and truncate the melting regime, and then we can see that ends at 5 kilobars, so that's what we're going to run today. Just like in pyusercalc, for your one-dimensional model run that saves at every step, you can put in a a porosity. Now in this case, it is not actually just a maximum porosity, it is the fixed threshold porosity value. And you can put in a solid mantle upwelling rate and your decay constants if you want to change any of those. All of them are put in line here because there is no separate script that you're accessing, so they all have to be right here in your notebook. The other thing you need to consider if you want to be reasonably realistic about dynamic melting is that for extracted magmas, you can impose a transport rate from the moment they are extracted at some depth until they reach the surface and are pooled into an aggregated melt. This is for integrating the results at the end. So you can retrieve your concentrations as initial values. You set your initial values, in this case using activities, so they're all values of 1 to set our activity ratios initially equal to 1. And then some other input values that you need that normally are automatically calculated on the back end for pyusercalc, but here need to be done in the notebook. So making sure you convert from depths in pressures to actual depths in kilometers, converting your units for your upwelling rates, etc. There are a few options here for setting up initial activities based on the inputs above. So you can set your ratios equal to 1 or retrieve them in a variety of different ways. And mostly I just have my initial ratios equal to 1 for uranium-thorium ratios, and the rest will all be retrieved from above. And then calculating initial concentrations is done right here for each nuclide that will be considered. Those are all saved to a run log. Now, and what's interesting about running this code, if you're used to pyusercalc, is that all of this is actually happening in pyusercalc, but you don't necessarily see it all because it's usually happening in the pyusercalc script. So here you actually get a little look under the hood, which can be fun. So now it's going to run the model. The try except is for in case you get an error. But this is the sample input, which is relatively straightforward. No error occurred, and it stored the results. So now we're going to process those results. We're going to save the instantaneous melt activities by calculating for them from the concentrations and decay constants. And then we're also going to get activity ratios. This is just the instantaneous result. And then we're going to need to use some values for our decay formulas if we want to integrate with extraction times. And then we're going to integrate them and allow the lavas or the magmas to decay as they're being transported and integrate the outcomes of that for all of our models. And then we're going to archive all of those results and view them. So we're going to build an output data frame and see what we got. The first row always has to have no data because there is no melt yet. So that's automatic for these activities. But the rest should be filled and should look correct, and it should look logical. If you want to see how logical it looks, we have some figures where you can view the outcomes. They're not changing much in this case. You can produce an equiline diagram showing the instantaneous first melt and then how they evolve over time. And you can now export that. And the last thing you can do are try a variety of phi values, of porosities and W values, which are your solid mantle upwelling rates. You have to build a bunch of information that's going to go into your figures and tables as you do this, and then you can run the calculation. So that was so fast that it already finished. And now we can actually generate our figures, which might take a moment because it has to access the external script. We are still going up here. So if you run these cells in advance, they will just wait until all of your calculations are done. Now, dynamic melting is a very stiff model, so it can be slower sometimes than even the disequilibrium porous flow, or it can be comparable to disequilibrium porous flow melting. It really depends on your inputs, but very stiff models do take longer to solve with adaptive stepping routines. So we will wait while this runs. If while you're waiting you want to see what is actually being saved, all of the cells that have these sort of two CSV commands are saving data outputs as CSVs, and then this comment is actually something you can edit, though the way it is currently written, it will automatically retrieve information from your run and place it in the header as an extra comment row in your exported data table. But you can modify that if you wanted to say something different. These figures are all saved with this save fig command. And they also are retrieving information from your runs for the names of the files that are exported. And they should look something like this when you save them. Let's see how we're doing down here with running the code. It looks like all of this has run. So you can generate contour plots for the different decay series, there and there. And then you can also generate different transport rates, if you like, and then you can also generate mesh diagrams. This error doesn't mean it hasn't saved. It's just a warning so that you know how postscripts are exported. So this one has no decay during transport. This one permits decay during transport, and you can see, depending on the value you put in this case 1,000 centimeters a year, that has a dramatic impact on radium, a much less dramatic effect on protactinium. So that's it for this tool. There is one other dynamic melting tool that's worth mentioning. It's much simpler, and it determines a simple analytical solution to dynamic melting, assuming constant melt transport rates and partitioning. And the reason for this notebook is really entirely for comparison with existing data sets in the literature. And so you can do a comparison between our more sophisticated dynamic melting script that can consider a variety of melting rates and productivities and partition coefficients, and the simpler solution that has been used in many cases. This version does not save anything at the moment. It is simply for viewing results as a comparison. If there is interest in being able to export from this, I'm happy to work on that, so please feel free to let the developers know. Thanks very much.